Hello folks, today we are going to be talking about using average atomic mass to determine the most abundant isotope for each element, which is covered under Unit 2, Standard 1F. Before we get into the nitty-gritty of what you are required to do, I want to provide you with some background information just so that you know where numbers are coming from and what they mean. So when scientists are looking at an element, they use a tool called a mass spectrometer to determine what isotopes of that element are present in a sample. So what that means is scientists charge the atoms, they give them an electrical charge, and then they fire them in a beam through a magnetic field. And heavier atoms have more momentum, and so they are deflected less by the magnetic field. And then lighter atoms with less mass have less momentum and are deflected more by the magnetic field. So, for example, if we look at chlorine, when you take a sample of chlorine and you run it through the mass spectrometer, it separates and you observe the two isotopes that are present. So the 35 atoms, the atoms with a mass number of 35, are bent more than the atoms with a mass number of 37. And so all the 35s pile up and all the 37s are in their own pile. And this allows scientists to compare how many of the chlorine atoms had a mass number of 35 and how many of the chlorine atoms had a mass number of 37. Remember that atoms can be of the same element even though they have different mass numbers, because what determines the element of an atom is the atomic number, or the number of protons, but the mass number includes protons and neutrons. So these two atoms of boron have the same atomic number, the same number of protons, which is 5, but they have different mass numbers. So some of the atoms have 5 protons and 5 neutrons, giving them a mass number of 10, but more of the atoms have 5 protons and 6 neutrons, giving them a mass number of 11. So you can see on the graph that there's more of boron 11 than there is of boron 10. And so when we're trying to take an average mass for boron, it's not fair to say some are 10, some are 11, 10 plus 11 divided by 2 is 10.5, because there's so much more 11 than there is 10, and this 10.5 average does not reflect that. So instead of taking a normal average, what we need to do is take a weighted average. Approaching the topic of weighted average, it helps to look at an example. So imagine that you're looking at a table of 4 students. 2 of the students are 16, 1 is 17, and the last is 18 years old. If we're calculating the average age of the students, we would get out our calculator and we would say 16 plus 16 plus 17 plus 18, and then we would divide that sum by 4, and we'd get 16.75 as our average. A couple things I want us to take away from this. First, even though we averaged in integers, right, whole numbers, our average came out as a decimal. So when averaging whole numbers, your average can be a decimal. Also, nobody at the table said they were 16.75 years old, but the average fell somewhere in between their ages. And because there were more 16-year-olds than there were 17 or 18-year-olds, the average landed closer to the 16, right, 16.75. So having more 16-year-olds dragged the average closer to 16. So let's look at an example that's a little bit closer to what's going on with atoms. Let's say we have a bunch of coins that have masses of 10, 12, 16, and 19. Right? Pennies, nickels, dimes, quarters all have different masses. And even with a small sample size like the one on the screen, it gets old really quickly having to add up all of those values and then divide by the number of individuals. And atoms are a lot smaller than coins. So if we were looking at 1 gram of carbon, there's 10 to the 23rd atoms of carbon in that 1 gram. And that is just too much, too many individuals to add each individual up. So how do we deal with this? So the traditional way of finding the average would be to add all of the values and then divide by the number of individuals. The first step that a lot of people take to tighten up that process and make it faster is, instead of doing 10 plus 10 plus 10 plus 10, they say, okay, well, why don't we just do 10 times 4? And then there are 6 12s, so we'll do 12 times 6. There are 3 16s, so we'll do 16 times 3. They do it that way. This does make it a little bit tighter, but it doesn't quite work with the graphs that we were looking at earlier that scientists have about how many of each isotope are present. So what they're looking for is a percentage that they can use. And so what we're doing here is we're taking the divided by 15 step and we are distributing it into each of our parentheses. So that the scientists can say, all right, well, 4/15 of our sample had a mass of 10, 6/15 of our sample had a mass of 12, 3/15 had a mass of 16, and 2/15 had a mass of 19. They standardize their denominators so that they're all out of 100, right? Because they're working with percentages. But this is what we would be doing in our example. This is the same way that your weighted semester average is calculated, right? So we take your score in the quiz grades, for example, and we multiply it by a percentage. And then we add it to your score in test grades times a different percentage. And then we add that to your score in classwork and homework times it by its own percentage. No matter how you calculate the average, if you do it correctly, you should always get the same answer. In this coin example, the average is 13.2. So let's go back to those graphs that scientists are working with and see how they do their calculations. So here's a graph that would come out of a mass spectrometer. It'll tell us that some of the atoms had a mass number of 20, 90% did. Some of the atoms had a mass number of 21, 0.27% did. Some of the atoms had a mass number of 22, 9.25% did. So what we do is we take the mass number, multiply it by the percentage of atoms that had that mass number, and then we add it to the rest of the individuals. So 20 times 9.48% out of 100, 21 times 0.27% out of 100, and 22 times 9.25% out of 100. If you do this calculation, you should get your average as 20.19, which tells us that this particular sample is neon. Neon's average is listed on the periodic table as 20.18, so we're very close to our average from this calculation. Now we're about to start talking about the steps that you are going to have to do under the standard in Unit 2. You are going to be asked to work backwards. So you're going to be asked to answer questions like this one. Chlorine has two stable isotopes, chlorine 35 and 37. If the average atomic mass is 35.45, which isotope is most abundant? So before we start talking about how to answer the question, let's take a moment and talk about what most abundant means. Most abundant is another way of saying the most common. So what this question is looking for is, of all the atoms of chlorine in the universe, are there more with a mass number of 35 or more with a mass number of 37? And we're going to determine that based on the average provided to us in the problem, but also on the periodic table. So just like with the 4 students in our earlier example, the average is going to be closest to the number that there is the most of. So our options here are 35 and 37, and we need to figure out if the average is closer to 35 or closer to 37. I find that the easiest way to do this is with the number line. It helps me visualize the process that I'm going through. So I put together a number line from 34 to 38 so that I had my answer choices on it, and I marked that 35 and 37 are my answer choices. Then I plotted the average, 35.45, on my number line. And once I did that, it was really easy for me to see that the average is closer to 35 than it is to 37. So we would report chlorine 35 as the most abundant isotope of chlorine. Let's look at one more example. If bromine has two stable isotopes of 79 and 81. Using the average atomic mass from the periodic table, 79.90, which isotope is more abundant? This average is very close to 80, which would be the halfway point in between 79 and 81. However, it is still slightly more closer to 79 than it is to 81. And when we plot it on the number line, that becomes more obvious than when we're just looking at the numbers listed in the problem. So because the average is closer to 79, even though it's only slightly closer, we would say that there is going to be more bromine 79 than there is bromine 81. Although the difference is probably going to be small because of how close the average is to the middle. All right, folks, so today in this lecture video we talked about where does average atomic mass come from, how is it calculated, even though you won't be asked to calculate it on a test or quiz. We also talked about why there are decimal values for average atomic mass, even though all of the mass numbers have to be integers. And finally, we talked about how you can use the average atomic mass to work backward and find the most abundant isotope. I've found another resource that talks about this, so I'll link that down below. But I do want to warn you that when you Google this topic, a lot of the results talk about how to do really complicated math that we are not being required to do. So if you're Googling help for this topic, please do not panic when you start to see lots of equations in algebra. We're not being required to do that. We're just being required to use the average to decide which of the isotopes that's listed in the problem is most abundant. And that's it. All right, thank you very much and have a nice day.